Okay, so hello, good evening. Good evening, all. So welcome to the first introductory session on wheel mobile robots. So I hope you are all enjoying the course so far. So I believe week two worth of contents already been uploaded in the have already been uploaded in the website. So so the purpose of these sessions, these sessions are just to you could consider these sessions as a refresher course, on weekly topics, and then to practice some problems, practice some questions uh, for the corresponding week, so that it'll be easier for you to crack the weekly quizzes and also to crack final certificate examination. So I am Isaac John. I am a PhD scholar from IIT Palakkad, and once again, welcome to the course on wheel mobile robots. So the course is actually jointly organized by Professor Shant Kumar Mohan of IIT Palakkad and Professor Ashokan Tondiyat of IIT Madras. So if you have reviewed the course contents, the first part, the first and last part, mostly dealing with mechanics and control of robotic manipulators, would be handled by Dr. Shant Kumar, and the topics concerning, localization and navigation will be covered by Professor Ashokan. So, without further delay, we shall start this live session. So, what I plan is, we'll since the session goes on for 2 hours, I thought it would be a good idea to just give to have a refresher of all the topics that we have covered. We had covered. We should be covering during week one lectures. I thought this was necessary because for courses for robotics courses, people from all disciplines would be joining. Not only from mechanical, people would be joining from electrical background. People would be joining from uh, CS background, all sort of backgrounds. So I thought it would be necessary for having a refresher sort of a thing at the initial part of the lecture. And during the later part of the lectures, we'll get on with the problem solving. You could expect more or less similar problems for the weekly quizzes. And please, there could be mistakes in the weekly assignments as well. So in case if you have noticed any sort of mistakes, during the weekly quizzes, if in case you have already started to attempt that, please let me know. You can always interrupt the session. Uh, I would prefer you to use the microphone. You should speak up because I probably may miss out, the questions through the chat. All right. So yeah, so this session is all about the topics that we have covered in week 1. So those include a brief introduction to mobile robots, as well as manipulators. What is the difference between a mobile robot and a robot manipulator? And then once we have comfortable with this, we would move on to locomotion and what are the different types of locomotion. And then in this week 1 itself, we start a basic introduction to mobile robot kinematics, which we would explore in much more depth in the subsequent weeks, in most probably in week 2. And then we will also learn the concept of degree of maneuverability. So that's probably it for week 1. So yeah, before we get on, like if in case you have any sort of issues in following me, be it my audio visual feed, or if in case if whatever I'm saying is not clear, or if you have any doubts, please feel free to interrupt. Okay, so we'll get on with the first topic for this session. That is just a brief introduction to robots and manipulators. So essentially, you could classify mobile robots and manipulators as something called effectors, right? So what is effector? So the definition of an effector is any robot or a robotic device that has an effect on the environment, right? Any sort of robotic device, any sort of mechanical interface or mechanical structure or mechanism that can have any sort of effects on the environment. So what are these effects actually? So effectors can be classified into two. The first being robotic manipulators and the second being locomotive device. And the key definition of a manipulator is that if the effect on the environment causes the motion of objects around, such effectors or such devices are called manipulators, right? Like for example, if you could consider an arm, a robotic arm. For example, if you consider a 2 degree of freedom robotic arm just like this. So if I call this as link 1 and if I call this as link 2, and at the end of the link, I have a gripper, a gripper to grasp objects. And I would fix the first link to the base. So the base would not be moving, but each of these links can rotate about its own axis. So a typical example of a robot manipulator, you could use a robot manipulator to pick and place objects. Or, robotic manipulators, you could find robotic manipulators in, assembly lines, for welding, for spray painting, vehicle bodies, vehicle chassis in an assembly line. So what robot manipulators are essentially doing is that they are simply manipulating the objects around. Maybe it has a tool, between its grippers. So it's basically manipulating a tool from one point to another. Or maybe it could be picking an object from one assembly line and it could be placing it on a separate assembly line. So in effect, irrespective of the tasks these things are doing, they are just manipulating the objects around. So that's what robotic manipulators do. And there are different classes of effector which are called locomotive device. So what these sort of devices do is that if their effect on the environment causes the motion of the effector itself or the effectors themselves, then such devices are called locomotive device, right? So if you consider a mobile robot chassis like this, so for the time being, you can assume it has four wheels, just like a regular passenger road car, a vehicle like this, right? So what effect can a mobile robot have on its environment? So if you give some input to each of these motors like so, and if you apply some torque on these wheels using some motors, the effect on the environment would be to create some tractive forces on the environment. And as a reaction, the entire chassis of the mobile robot would move forward or move in any direction depending on the relative speed and relative direction of the wheel velocities. So the effect on the environment causes the motion of the effector itself. Right? If you are putting some tractive force, due to that, as a reaction of the tractive force put into the environment, the device achieves locomotion. So such sort of class of devices or such sort of effectors are called locomotive devices, right? And the key distinction is that manipulators, they are basically fixed to the ground, and locomotive devices, they are unrestricted, like they can move anywhere in the environment. So yeah, here basically you can see an example of an industrial manipulator, right? It could have multiple degrees of freedom, like it can rotate about this vertical axis, it can rotate about this axis, it can rotate about this axis. 3 degrees of freedom already, and these part, it could have 3 degrees of freedom. It can move up and down, it can move side to side, or it can roll about this axis. So this is how a 6 degrees of freedom robot manipulator would typically look like. The 6 degrees of freedom be, three positional coordinates and three orientational degrees of freedom. And this is how a typical mobile robot or a locomotive device would look like, right? So as you can see, already you already have some sensors, external to the robot, to ultrasound sensors, or you could also have a camera sensor, you could have a lidar sensors. But in case of a robot manipulator, it's basically clean. It does not seem to have any sort of outward sensors. So let's look at a key distinction between manipulators and mobile robots in further depth. So manipulators, these devices operate in a constrained workspace, right? Like as I've said, most oftenly their base are always fixed. They'll be always fixed to a location, and as a result, it can only reach a workspace. If, for example, like if you fully stretch your arm, you cannot go beyond your fully extended position of your arm, because if you consider your shoulder to be fixed, you cannot reach any further point beyond the fully extended position. So in that regard, your workspace is actually constrained in case of a robot manipulator, and you could have absolute measurements of position, right? Because each of these joints, they have these joints, individual joints are actuated by its own motors, and each of these motors are coupled to their own encoders. It's a sort of it's a sensor, basically to obtain the orientation or the angular displacement of each of these joints. So due to the fact that the motors are coupled with the encoders, depending on how the relative motion between different links occur, you can basically have absolute position. And that is the second point. And for the third point, they may or may not need to perceive the outside world around them. So depending on the situation, it may need to perceive the environment, or in some other cases, it may not even need to perceive outside environment. Like for example, if you consider an industrial situation, in an industrial situation, the entire workspace of a robot manipulator would be fixed. The obstacles are all fixed, or the robot would already know where each of its points of interest are, where each of these objects are. It will know in advance, how to navigate through its how to navigate through the workspace. So if it already knows in hand, it does not require any sort of external sensors to perceive the environment around them. It can basically, operate in blind, basically. But there could be some situations where where the obstacles within the robot's workspace could be dynamic, right? Like for example, if there is a robot which collaborates with human beings, a highly collaborative robot, the robot will have to adapt its trajectory depending on the position of the human beings within its workspace. Otherwise, it will be very dangerous for human beings. And similarly, for robots that are collaborating with each other, a multi-robot system, each of the robots will have to adapt depending on the other robots in the system. So in that regard, it may need to perceive its environment to avoid any sort of mishaps, or if it wants to collaborate with other robots, it may need some external sensors like probably vision sensors, proximity sensors. So yeah, we can have multiple scenarios. It can have sensors to perceive the environment, or it may not need to perceive the environment depending on the application, as I've just mentioned. So whereas in the case of a mobile robot, they can operate in an unconstrained environment. They are free to explore the environment. Like they are not constrained to any point of the environment. Like they can move wherever they want. And as a result, they need external sensing to determine its position. So since its workspace it's unbounded, we cannot have a static workspace because things keep on changing. As the expanse of the workspace grows, the relative position orientation of all the obstacles within the workspace basically changes. So in that regard, it may need to perceive objects around it, right? Otherwise, it will simply go and bump into obstacles, or it may simply go into some undesirable spaces, or it may get itself trapped, or it may even get itself lost, and not knowing where it is basically. So it's absolutely essential for a mobile robot to know its position. So it can be done with using its internal sensors, just like how the manipulators as encoders. But on top of it, it also need external sensors, like this ultrasound sensors, vision sensors like stereo cameras, lidars, all sort of things. And it also needs sensing to avoid obstacles. So like apart from detecting its own position, it also need external sensors to avoid obstacles, to avoid collision with obstacles. So those are the key differences between, robot manipulators and mobile robots. And notice how the wheels of this mobile robot looks like. It looks sort of unconventional, right? It has a cylindrical shape on the inner periphery, but on the outer periphery of the wheels, it has this inclined barrels, inclined rollers, like so. So yeah, maybe in the upcoming week, we will actually see the mechanics of these sort of unconventional wheels, and how these sort of wheels enable the robot to move forward, backward, or it can even move laterally, like so. It can even move diagonally, just by keeping its orientation fixed. Like these sort of things has very high degree of maneuverability. So all these things we'll see in the upcoming weeks, how to model the kinematics, or how to model the mechanics of, highly unconventional wheels, like so, like the one I've shown here, right? Okay, now moving on, we are still at the introductory part of robots. We still haven't targeted ourselves in mobile robots. We are still on the, on the introductory part. So Now, this slide basically says when and where to use robotics. What are the feasible applications that where we can use robots. So traditionally, earlierly, when we started deploying robots in applications, earlier we have been using robots in tasks that can be classified as dull, dirty, and probably dangerous. Dull tasks probably, it could be a very dull task for a human being. Earlier in assembly lines, human beings are involved. Human beings are basically involved in each and every stages, to tighten a screw or probably to, insert a bearing and then to take that part to put into an assembly, a different assembly line. So these are repetitive and people will have to do this thing repetitively for probably more for a large number of hours, and it can easily become very tiresome. So those sort of jobs, dull, very dull and very tiring jobs, then jobs that are dirty and probably dangerous. Dirty in the sense like, it's not, for example, if you take a look at this manhole cleaning robots or sewer cleaning robots, those tasks are basically not suitable for a human being to do because it's usually considered as a dehumanizing job. But with the advent of robots, you can basically replace a human being to do all these sort of jobs, so that a human being does not have to be exposed into dirty or even dangerous working conditions. Like for example, in case of sewers, poisonous gases, very dense poisonous gases could get accumulated at the bottom of the sewers, and since they have very high density, they cannot be easily pumped out, or they cannot freely flow out from a very deep pit or a borewell or probably a sewer. So if you deploy a human to clear those things, it could be very dangerous because there could not be any oxygen, which would be displaced by this heavy gases, and it could probably lead to loss of consciousness and eventually the death of human beings. And then, later, with the advent of more computational capabilities, we started to deploy robots on dull, dirty, dangerous, and difficult tasks. You know, because tasks that are difficult even for a human being, it could be much, much difficult for a robot to perform, right? For example, if you consider walking, it's far more easier for a human being to walk. We learned walking at a very young age, but walking for a robot, designing a bipedal robot and to make it work in a very robust manner is actually pretty difficult because it requires a lot of computations. Yeah, computations actually huge. If you want to incorporate something in real time, the amount of computations to make a stable, biped robot is probably going to be very huge. But with the advent of more and more advanced computational systems or much more developed computational systems, those things are now being feasible these days. So even difficult tasks, maybe we can manage with robots. And in modern cases, we can use them for dull, dirty, dangerous tasks and tasks that are dear. So dear means essentially tasks that is expensive if you deploy a human being, right? So as if you are deploying a human being for a task, labor charge is actually a huge part of it, right? Maybe except in countries like India and China, because that's why more people are basically coming to countries like India and China to set up companies and workshops, because labor charges are comparatively low when you compare it with Western countries. But typically, labor charges are very detrimental. If you want to start a a very high turnover companies. So you these days, people a lot of tasks are being really viable if you can replace the human labors with robotic technologies, right? Even though the initial capital to invest in such technologies, even though it's very high, eventually, after a long while, not even a long while, after a while, it will break even, and you will see profits. If you replace, a vast number of human forces with robotic systems, it will break even. And currently, the current trend is all about dull, dirty, dangerous tasks and tasks that are domestic and dexterous. So robots have infiltrated in tasks that could be classified as domestic. For example, the robots these days, the Roomba robots, the vacuum cleaners, or those, you could probably find them in a lot of homes these days. So they have basically the robots have the adaptability to work in a domestic environment, without harming the human beings or without harming their properties. They are now well integrated within a domestic applications. And similarly, there are lots of service robots also. Uh, in place of service animals, we can have service robots which work in very close proximity with human beings, uh, with differently able human beings. And then robots are also deployed for tasks that are dexterous. You would most often see this term dexterous in the manipulator community. So what dexterity means is that, like, if you have a point in workspace, and if you can realize that point in any sort of orientation, in all sort of orientation, then such points are called dexterous points. Right? For example, if you consider the tip of this pen as a workspace, and if you consider the tip of my arm as the robot's gripper, I can basically reach this tip of this pen at using, with any possible orientation. So those points are basically called as dexterous points. But there are points that are not fully dexterous. So one example is that, like, if you fully stretch your arm, the point that you reach with your fully stretched arm, you can only reach with that single orientation. You cannot reach that point with any orientation. And the same thing goes for the point when you close your arm, when you fold your arm fully, because you can reach that folded point only in one orientation. So even though those points are reachable, those points are not dexterous. Right. So that's what the word dexterous means basically. Okay. So now that we have covered, basic differences between, manipulators and mobile robots, now we'll, uh, uh, dive a bit more deep into mobile robots, because that is where we wanted to, take, or where we want to proceed our course into, right? So, like, we are not really there yet. We are not into wheel mobile robots, but we are getting there. We are now covering mobile robots. So what is a mobile robot? So mobile robot is an autonomous machine, or an automatic machine capable of locomotion. We have seen what locomotion means. It's not fixed to any location. That's fair enough. It can roll, walk, fly, or swim. So, like, locomotion can be realized in any of this manner. It can roll. There are robots that can roll. The robots can walk. The locomotive devices can walk. You have all seen these quadruped robots. This dog-like robots that can basically walk. There are humanoid robots that can also walk. There are robots with one leg that can. You cannot call them to be walking. Those can hop. One-legged robot. Those are hopping robots. Then there are robots that can fly. We call them unmanned aerial vehicles, drones. They all come under robots that can fly. And then we have robots that can swim. Underwater robots, or water surface robots, which won't go under the water, but they'll float on the surface. And then there are submarine sort of robot which can, which has all 6 degrees of freedom, which can go under the water or under the ocean for exploratory or intervening purposes. And they are typically less structured in their operation and are likely to use more sensors than robotic manipulators. So, like for the reasons that I've told earlier, since their workspace is unconstrained, the environment is actually pretty dynamic. So, in order for them to adapt to a dynamic environment, they are required to use more number of sensors when compared with a robotic manipulator. So yeah, that's about a mobile robot and the different modes of mobile robot, different modes of locomotion for a mobile robot. And then the fundamental problems of a mobile robot, what are the fundamental problems that are addressed by a mobile robot? So the fundamental problems can be formulated as these three questions. Where am I? A mobile robot is asking uh, uh, these questions to itself. Where am I going, and how do I get there? So these are basically the purpose of a mobile robot. So how do you answer this question? Where am I? So to answer itself, where its position is or where its current location is, it has to make measurements and model the environment. So as you will see in the subsequent weeks, there are two ways that it can do. It can localize itself. Either you can give a map to the robot so that the robot can download the map, or it can already preload the map, or there are cases where it can create its own map on the go, right? As it is exploring the environment, it keeps on updating its map, or it keeps on improvising its map. So two approaches are possible. Yeah. So once it has a finite map, then the next thing it has to do is it has to see where it is going, though. Where am I? So, like, since it has already addressed where am I, it basically, we can assume that it already has a map. Whether it is being given to it or whether it has made a map on its own. The next question to address is where am I going? And the answer to it has to localize itself, right? The reason is that even though it has a map, for example, if you consider this as a map, and if this is the current position of the robot, but it does not know where its position is. It has a map, but it's not really sure where its relative position of the robot is. And for example, if you have a target position, maybe I'll call this as a goal position. I hope it's visible. So the first task is actually to create the map. Uh, Hold on 1 second. Yes, sorry about that. So I hope my screen is still visible. Yeah. So the first task is to create a map. Then the second task is to identify its position. It should know where its position is on the map it just created. So that process is called localization. To identify itself or to figure itself its position within the map it just created. It's called localization. So now that it has its own map, it also knows its position in the map. The next problem to address is how do I get there? How do I get to the goal position? So to get to the goal position, it has to plan a path to its goal and then control its motion. Right? It'll have to plan an ideal path. It could be a straight line, or if there are obstacles around it, it'll have to, take a curved path, or it'll have to adapt around the obstacles. It'll have to take an optimal trajectory based on some optimal conditions. We will see that in the subsequent weeks. Yeah. So once it has planned its path, uh, so the controller will basically, will decide which path to take, how to avoid the obstacles, what is the optimal path to take. And once the controller has taken that decision, it will pass on the instructions to the motors or to the actuators so that the robot can actually start moving. so that it will basically, follow the desired trajectory and it will reach its goal point. So these are the fundamental problems that a mobile robot tries to address. And yeah, then we've also seen the subsystem of a mobile robot. What are the different subsystems? The first subsystem is the locomotion. How a robot moves through the environment. So, like in case of a mobile robot, it can have multiple locomotive systems, just like I've said earlier. It can fly. It can, if its application is in water, it can have the robot could be having some underwater thrusters so that it can navigate inside a water body. It can it can have terrestrial locomotive solutions like walking, hopping, and probably rolling with wheels. Those are all examples of different locomotive solutions. And the next subsystem are the sensors. How the robot measures the properties of itself and its environment. So the properties of itself is, as I've mentioned earlier, to localize itself, it has to learn about its own position using the sensors that it has. It has sensors within the robot. It also has sensors, that perceives the environment. So using those sort of sensors, it needs to know its position and it also needs to perceive its environment, to avoid all the obstacles. And then the third subsystems is the reasoning subsystem, actually, how the robot maps the measurements to actions. So whatever sensors, whatever data it acquires from the sensors, it has to convert it into actions. The controller will, take an informed decision based on the data from the sensors, and then it'll be converted into actions. So that's what a controller does actually, how the robot executes its planned actions. So the controller will deliver the planned actions to the actuators. And according to the desired control input, the actuators would start moving and the robot would move accordingly. And the final subsystem are the communication module, how the robot communicates with an external operator. You could have multiple ways of communication. You could communicate the robot with a remote. If you press the forward button, it will go forward. If you press the backward button, it would come backward. Or you could have, it could have fully autonomous control where a human operator need not be monitoring at all stages. It might only need to intervene when the robot is in distress, or probably when the robot is completely at lost about its own position. So to help those sort of situations, a human operator can intervene. But for all these purposes, and there has to be some sort of a communication between a mobile robot and an external operator. Okay, so that's about the subsystems. And what are the key issues in locomotion or the key challenges? So the most important challenge is the stability. The stability of a mobile robot. So, for example, if you consider a two-legged robot, in case of a slightest disturbance, it's very probable that it can fall over. Right? If you try to push a two-legged robot, it'll basically find itself very difficult to hold its position. It will most probably topple over. And the stability is a function of a lot of points. The most important ones are the number of contact points, the center of gravity, and the static and dynamic stabilization and inclination of terrain, so on and so forth. Right? If you want to know more about the number of contact points, I'll give an example. Like if you have a mobile robot with four wheels, if the level or if the ground is not perfectly level, right? If it is not purely planar, then it'll probably wobble. Like one example I can give you is that, like if you, for example, if you have a four-legged chair or a four-legged table, so if the ground is not perfectly level, and you might have observed, the chair might wobble because at an instant, you only require 3 points to be in contact. right? Because you only need 3 points to fully define a plane. And the fourth point will basically, hang somewhere in the air. And depending on how you shift the weight, that the point can, get into contact, and as a result, some other point could be up in the air. So like it keeps on wobbling. So that is a key issue actually. Stability is a key issue, not just for legged robots, even for wheeled robots. Even if you have four wheels, due to these inherent issues, it can have stability issues because of the point of contact. Center of gravity is actually a huge factor. For example, if you have a robot like this, very short and very, it's not that tall, and it's very wide, and its center of gravity is actually very close to the ground. For example, if you have a robot that is a bit tall, like this, if you consider these to be the wheels, and it has very high center of gravity, and if this sort of robot is moving in this direction, and it is suddenly coming to stop, there is a high probability that these sort of robots will topple over because of this high center of gravity. And center of gravity is an issue. And the other key issues, you could consider those to be, static and dynamic stability. For example, in case of a legged robot, if, for example, in case of a legged robot, there are two phases. We usually call them, swing and steady phases. For example, if the two legs are in contact with the ground like this, if you consider this to be probably a humanoid robot, when two legs are in contact with the ground at an instant, we call it as a static phase. And you can probably, it's probably far more easier to balance a robot in a static phase. But during the swing phase, only one of the legs would be in contact with the ground and the other leg would be swinging. So that is an inherently unstable phase, and you would have to, design your controller, or you will have to design the parameters in a such a way that it'll also have some sort of a dynamic stabilization process going on. You can consider the dynamic equilibrium of the systems, right? So those are mostly, an issue of legged robots, especially biped robots. Then another issue regarding locomotion are the contact characteristics. The area of contact, the angle of contact, the friction, right? So in mobile robots, friction is most probably more often a good thing, right? For example, you can probably see, a snake or a lizard would find it very difficult to crawl through very slippery surfaces like tiles and all those things. So robots can also, similar problems can be faced by robots actually, because lack of friction. It may not be able to generate the necessary tractive forces or necessary, forces to propel itself. So those things comes under contact characteristics, and then the type of environment is also, a huge factor. Whether the environment is engineered, like interior of a building with tiles with very smooth surfaces, or if it is required to operate outdoors, you know, like for example, you might have known how the Mars rovers, the rovers that we have sent to Mars, the surfaces and the environment is actually extremely harsh, extremely hostile. So in that cases, depending on the environment, we'll have to adapt, the type of locomotive systems that we would be using. We wouldn't probably send a robot with wheels to those sort of environments, right? Because wheels may not generate the necessary amount of tractions. Instead, we'll have a system that has tracks, what we call tracks. You might have seen them in military tanks, right? Those are very rugged. Those, it can be deployed in very rugged environments. Okay, so now that we have moved on to mobile robots, now we will narrow our discussions to land-based mobile robots. right? Apart from aerial, underwater, mobile robots, we'll restrict ourselves to land-based mobile robots. And within the land-based mobile robots, we have several classifications. The first one being wheeled mobile robots. That is the topic of our course. Apart from wheeled robots, we have tracked robots. Just the example that I've just mentioned. The extraterrestrial rovers. Those are tracked robots. We have legged robots. Human. We can have humanoid robots. We can have quadruped robots. We can have hexapods. We can have many number of legs, and we can have hybrid robots. We can have robots that has a combination of wheels and legs, just like an example I've shown here, right? So these sort of arms, they can act like wheels, as you see. So the bottom two arms, those two things basically act as a wheel. So when it encounters an obstacle, or if it encounters a step, these arms will act like any normal wheel. It will basically lift itself over the obstacle. It can basically lift itself over the obstacles because that's what legs do, right? And once it has cleared all the obstacles, it can move to a wheeled configuration, right? So these wheels would start working once it reaches a very smooth environment. So it has advantages of both wheeled as well as legged systems. So those are hybrid land-based mobile robots. Okay, so that's about a basic introduction. Now we will move on to mechanics, and under mechanics we'll start with kinematics. So basically, kinematics is basically the study of motion without considering the forces that affects or that causes the motion, right? So the key word or the broader word is actually mechanics, actually, basically. And under mechanics, we basically have two subclasses. We call it as statics, and the other sub section is dynamics, right? And in statics, the entire subsystem would be in equilibrium. It does not have any unbalanced external forces. All the bodies or all the systems involved in a robotic system will be under equilibrium. It'll remain static, and it's not under an action of any external forces. And under dynamics, we have two more subsections. So we call them as kinematics, and the second being kinetics. And this is where we are focusing our attention currently. So kinematics only deals with motion. It only deals with motion, but it basically ignores what actually causes the motion, right? For example, like if you consider this an object at rest, and you're applying a force, and due to this unbalanced force, it'll achieve some acceleration, and eventually, due to friction and probably air resistance, it eventually comes to stop. And in kinematics, we are only studying the motions. We do not or we ignore the external effects that causes the motion, or we basically ignore the interaction between different bodies that causes the motion. But in kinetics, we consider everything. We consider the forces, we consider the torques that actually causes the motion. So we'll study this in depth in subsequent part of this course. But for the time being, we'll basically we'll basically restrict ourselves to kinematics. So so the first definition that I would like to introduce is something called the degree of freedom. Right. So basically, the degree of freedom is the minimum number of variables required to describe a system. Right. So what does it mean by that? So if you consider any rigid body in an environment, in a space, how many variables do you require to fully describe its configuration or to describe it? So basically, you need 3 points with three coordinates for its position, right? To three coordinates to fully describe its position, and you need three more coordinates to describe its orientation, right? It can rotate about the vertical axis, it can rotate about its longitudinal axis, or it can roll up and or it can pitch up and down. Three rotations. So generally, for any rigid body, you require 6 degrees of freedom to fully describe it. But in case of robots that moves within a plane, you only require 3 variables. Like for example, mobile robots operate in a plane, right? In a plane at which it is moving or it is locomoting. So for example, if you consider the plane of this slide as the plane of interest, you can I'll fix a coordinate frame on it. You know, I can call this as a y-axis. I can call this as an x-axis. And the z-axis would be out of the plane. It will be perpendicular to the plane. And here you have a mobile robot chassis. I'll redraw this at a different orientation like this. Like this. So the question is, how many variables do you need to describe its to describe this mobile robot? You would need 3 variables, right? You need 3 variables. 2 variables for position. I'll label this as this is the y position, y coordinate, and this is the x coordinate. So you require 2 positions, which are x and y coordinates. And you require one more coordinate. I'll call that as theta to describe its orientation. Right? So this theta is referred with respect to this x-axis, with respect to this horizontal x-axis. Because even if you fix x and y, it can be oriented like this, and it can be oriented like this, it can be oriented like this, right? So an xy is not enough to fully describe its orientation. You need one more coordinate. So one orientation coordinate, which is described by the parameter theta, right? So for mobile robots, which basically operates within a plane, you require 3 degrees of freedom or 3 parameters to fully describe its configuration. Whereas in case of any spatial robot, any generic robot that lives in space, such as aerial robots or underwater robots, you need 6 degrees of freedom, right? 3 for position and 3 for orientation. Okay, so with that, we will talk about frame assignment on, frame assignment on mobile robots. But before that, are there any doubts or are there any questions that you would like to ask? Because I feel like I've been talking for 1 hour, but I'm getting no feedback from the viewers. Okay, so I hope there are no doubts. I'll continue with I'll continue with the topic. So now that we have described that a mobile robot or a wheel mobile robot requires 3 degrees of freedom, how would you make use of it? So typically, we would have a frame of reference fixed to the ground. So if you consider this plane of the board as a ground, I would fix a frame of reference like so. This is the x-axis. This is the y-axis. And since this is fixed to the ground, I could call this as an inertial frame of reference, where the Newton's laws are valid. And somewhere within somewhere within this ground, I have a mobile robot. I'll draw it in a random orientation like this, right? And I would fix the coordinate frame on the mobile robot, like so. So I'll call this as frame X. I'll have a suffix B because this is fixed on the body of the mobile robot, YB. And I'll call this frame as the body fixed frame Y. So this is very convenient because, in case of a rigid body, if you have a rigid body like this, the defining feature of a rigid body is that the relative position between any 2 points of the rigid body will always be fixed. It won't change. For example, if you consider these 2 points, their relative position and orientation will always be fixed. No matter what happens, it'll always be fixed actually. So to represent a rigid body, it's far more easier to represent a rigid body with a coordinate frame, right? So this rigid body, we can basically describe the rigid body by using a coordinate frame that is attached on this rigid body. It can be attached anywhere. You can attach the coordinate frame here. You can attach here. You can attach on the centroid, or you can attach it at the center of gravity. Whatever be the case. So how do you describe a rigid body using the coordinate frame? You can use the position of this origin, position of the origin of the body fixed frame with respect to this inertial frame to describe the position of the entire mobile robot, right? If you know the position of the origin of the body fixed frame, you can basically find each and every point of the rigid body, because as I've said earlier, the relative position between any 2 points of the rigid body is always going to be fixed. So the position of the rigid body can be described by the position of the coordinate frame, and the orientation of the rigid body can be described by the orientation of the body fixed frame with respect to the fixed frame, the ground fixed frame, right? So for example, if you consider the relative orientation between the x-axis of the ground frame and the x-axis of the body fixed frame to be an angle theta, the relative orientation between these two frames, you can consider it to be theta. Theta in the counterclockwise sense, right? So if you basically rotate this inertial frame counterclockwise by an angle theta, you will get this orientation. Okay, but how this is relevant? Why fixing a body frame of reference is useful for us? Why should we bother? Why is it useful for us? The reason is that we give control inputs to the mobile robot. We are basically giving control inputs to the mobile robot, right? For example, if it has wheels like this, for example, if you consider it has two wheels, you are basically giving the control input to the mobile robot. And a mobile robot is something that keeps on moving at every instant. So to define the control inputs or to define how a mobile robot moves, it's much more easier to give the inputs in the body fixed frame. It's much more easier to give control inputs in the body fixed frame, right? But to observe the motion of a mobile robot, it's much more easier to observe in the ground fixed frame, right? So like if you create a mobile robot, you deploy it on the ground, but you observe the mobile robot from the ground, right? You cannot be inside a mobile robot and make observations. You would be on the ground, but mobile robot would be basically moving around the ground. So for observing, it's always ideal to observe the mobile robot with respect to the ground reference frame. But to give the inputs, to give the commands to the mobile robot, it's much more intuitive, or it's much more easier to give the controls with respect to the body fixed frame, right? So since the mobile robot has 3 degrees of freedom, we can basically give three inputs. The first input I would say would be the velocity along the xb direction. I call this u, you know, velocity, the command that we give to the robot so that it can move along the xb direction. We can give a command along yb direction. I call this as v. And we can also give a command so that it can rotate about its own axis. I'll call this as theta. Sorry, I'll call this as r. So I'll just label what these are. U is nothing but the velocity. For these are linear velocities actually, linear velocities along xb, and v is the linear velocity along yb, and r is the angular velocity along zb, because the rotation would be always about the perpendicular z axis, that is out of plane, right? And in the later in the subsequent weeks, in the upcoming weeks, we will see how to map this UVR, to map this velocities in xb direction, the velocities in yb direction, and the velocities in r direction as inputs to the wheels. You need one more mapping so that this UVR can be mapped to the angular velocities of the wheels, right? And that depends on the configuration of the wheels you have, right? For example, if you have a mobile robot with 4 wheels like this, you will have a different mapping. You will have to find the angular velocities of each of these wheels so that it can achieve a desired U, V, and R. And similarly, there are a lot of different configurations of wheel mobile robot. For example, the one with the unconventional wheels that I've shown at the beginning of the lecture, it will have a different mapping. But we'll see that in the subsequent lectures. But the time being, our requirement is that the mobile robot should have u velocities along xb, v velocities along yb, and an angular rate of change of speed r along zb. And now what we want is we are going to map this UVR to the ground frame of reference. For our sake, because it's easier for us to, because this is how our perspective would look like. Our perspective would look like from the ground frame of reference. So how do you map? So if I call the variables, if I call the velocities along the fixed x-axis as x dot, and the velocity along the fixed y-axis as y dot, and the angular velocity along the fixed z-axis to be psi dot, you want to find a mapping between x dot, y dot, psi dot, and between u, v, and r. Just to find the relative, just to find out the mapping between the parameters in one coordinate frame to the other coordinate frame. So this is just a basic, simple thing. So what I can do is I can basically superimpose these two frames. I'll do that in a minute. So if I call this the y-axis, if I call this as the x-axis, and the velocity is y dot, and the velocity is x dot. And if I superimpose the body fixed frame onto this, just for reference, so this is the xb axis, the velocity is u, and perpendicular to the xb axis, we have this yb axis, and the velocity is v. And the relative orientation between these two coordinate frames is given by this parameter theta, right? I'll call this as theta. So how do you resolve, u and v along x and y axis. So I'll label this as x dot is nothing but, the component of u, if you take the component of u along x dot axis, that is nothing but u cos theta, right? And this v will also have a component along this x axis. What is that component? So if this is theta and this entire angle is 90 degrees, this would be 90 minus theta. And since this is 90 minus theta and this entire angle is 90 degrees, this would be theta, right? So the component of v along x-axis is minus v sine theta, right? That is nothing but minus v sine theta. Like if you have any sort of issues, if you have any doubts, please let me know. I can explain it once more. And similarly, y dot, the component of u along y-axis is u sine theta. This component is nothing but u sine theta. So that is u sine theta. And the component of v along y-axis is this component actually, that is nothing but v cos theta. That is plus v cos theta. And since the z-axis are always aligned, the z-axis of the ground fixed frame and z-axis of the body fixed frame are always aligned, you can basically have this relation, the psi dot is always going to be r. Because both of the z-axis are always going to be aligned. So you can basically write this mapping in a matrix and vector form like so: x dot, y dot, psi dot is, cos theta minus sine theta, 0, then sine theta, cos theta, 0, and 0, 0, 1. This multiplied by u v r. I hope I am clear with this. If I'm not clear, please let me know. I can try to elaborate this in a more detailed manner. Multiplied by u, sorry, u v r. So the mapping between this x dot, y dot, and psi dot with respect to the fixed frame of reference to UVR, the velocities in body frame of reference, is given by this matrix. Now we call this as a Jacobian matrix, matrix J, right? So that is the basic fundamental aspect of kinematics. You need to know, how we can map the velocities in the fixed frame of reference to the velocities in the moving frame of reference. Because mostly we would associate this vector as the control input, right? The control input that we have to give it to the robot. And we associate this as our desired trajectory. We associate this to our, the desired velocities. And to achieve this desired velocities, we associate this vector to be the control inputs, right? And you can express this matrix and vector form in a compact form like this: eta dot as j of psi multiplied by zeta, where eta dot is this vector and zeta is this vector and Jacobian is this matrix, right? And each of the terms are basically labeled like so. X, Y, and psi are the forward, lateral, and angular displacement with respect to the fixed frame. U, V, R are basically the forward, lateral, and angular velocities with respect to the body frame of reference. And psi and eta are simply the names that we give to these vectors, x dot, y dot, z dot, and UVR. Okay, so now that we have established, the kinematics, the kinematic mapping between uh, two frames, eta dot and psi, there are two problems of interest that we would like to solve in kinematics. So the problems are, the first one we call it as forward differential kinematics. So in this problem, we give an input to the robot. We give UVR inputs to the robot, and then we observe how the robot is moving in its environment, right? So this process is equivalent to simulating or analyzing the mobile robot in velocity level, right? The forward problem is basically simulating the robot in velocity level. So the thing is, if you are giving some input, how would the robot move? That's just like simulating, right? Any simulation cases. But there is also an inverse problem. We call it as an inverse differential kinematics. So the problem is finding the velocity input commands for desired derivatives of generalized coordinates. So if eta dot, if we want the robot to move in a desired manner, that is described by the elements of eta dot. For example, we have a desired x dot, we have a desired y dot, and we have a desired psi dot. These are our desired coordinates or desired velocities. What should be the input that we are required to give to the robot? For a desired motion, what should be the input? So that problem is inverse differential kinematics. And finding out, this zeta from eta dot is inverse differential kinematics. So what we do is we find the inverse of the Jacobian and we multiply that to our desired vector. So like this is similar to controlling the system at velocity level. Earlier it was simulating and now it's controlling. We want something, we want a desired trajectory. What should be the input? So that is basically controlling the robot at velocity level. There are a few more things that I would like to discuss. The thing called degree of maneuverability. It's nothing but the sum of degree of mobility and steerability. And what the definition of degree of mobility, that's nothing but the degree of freedom the mobile robot manipulates directly through its wheels. So like, for example, if a robot has a powered wheel, then it will add the mobility by 1. And we have a degree of steerability. It is a degree of freedom that a mobile robot indirectly manipulates by changing the steering configuration. So like if we have a wheel and it can, we are giving an input to change the steering angle, then it will increase the degree of steerability by 1. And the sum of degree of mobility and sum of degree of steerability is the maneuverability of the robot, right? And we have also seen in the lectures, the different kinds of wheels. We have this fixed wheels like so. You can have powered fixed wheels, or you can have, unpowered or passive fixed wheels. Like for example, in case of a bicycle, the front wheels are conventional wheels, but it's not powered for the front wheels of a bicycle. And the green thing basically denotes it's passive, right? It's not powered. So these are not powered. I call this not powered. And the red color depicts it's powered. Those wheels are powered. And there are wheels that are rotatable, right? So these wheels are basically, powered and steerable. Powered plus steerable. And these are neither powered nor steered. Just like in the examples of a shopping trolley cart. So the defining feature of a conventional wheel is that, in the mathematical models, for a conventional wheel, like a car tire or a bicycle tire, you assume infinite resistance along the lateral direction. The infinite resistance. It cannot support any sort of motion, in the lateral direction. So if this is the, plane of motion of the wheel, and if you call this as the hub of the wheel, this is where we have the axle of the wheel. The direction parallel to the hub or direction parallel to the axis is the lateral direction. And conventional wheels are assumed to have infinite resistance along the lateral direction. And now we have these sort of, unconventional wheels. You call this as mechanism wheels. And this one is called omni wheels. And in case of mechanical wheels, as you can see, at the periphery of the wheels, you have these sort of passive rollers, inclined passive rollers. And due to the presence of these inclined passive rollers, these wheels are actually, free to move along the lateral direction. And it does not have any resistance in the lateral direction. So the wheel, it's like a wheel that can move forward and backward, but it can also move side to side. And same in the case of omni wheels, they have this, passive rollers, that is perpendicular to the axis of the hub of the omni wheel. And due to the presence of this omni wheel, the omni wheel can rotate like a conventional wheel, like its own axis, but at the same time, it can also, transverse laterally, side to side, due to the presence of these rollers. And each of these kinds of wheels and their arrangement, they'll contribute to different mechanics. Okay, so yeah, that's about the topics that we have covered. A brief summary of the topics that we have covered. So now that we have covered a refresher, or now that we have had a refresher for the contents of this session, we can solve some sample problems. And please note that these sample problems are, very similar to the questions that you can expect during the weekly quizzes. And you can also expect more or less similar questions for your final certificate exams. Right? So I think I may have a few questions. We can solve them one by one. So I would expect some active participation from the participants if you are all online. Can we have a, a mic check, please? Is there anyone online?
It's a locomotive device.
Should I wait for a few minutes so that you can solve the problem, or should I, solve it on my own? Which method should I adopt? Okay, I still have no answer from the audience. Am I audible?
Yeah, it's a locomotive device.
Oh, okay. The one thing was that I had a mistake. My volume was actually very low, so I might have probably missed all the conversations that you might have had, probably in the during the course of the session. Yeah, I have just turned up my volume, so I'm sorry if anyone tried to interrupt me, or if anyone tried to uh, you know engage in a conversation. I completely missed those. Okay, and now I'm getting some answers. They are called. Yeah, the answer is actually locomotion. Locomotion devices or locomotive devices. So you can expect these sort of fill in the blanks questions for your quizzes. Yeah, so the answer is indeed correct. It's locomotive devices. But most probably you wouldn't worry too much about fill in the blanks, because you can get fill in the blanks for numerical questions. Descriptive questions can always lead up to some confusion. Some people can write locomotion like I've done, but the answer key is actually locomotive. So that can probably cause some unnecessary confusions. But yeah, numerical questions, you can probably expect fill in the blanks for numerical questions. So that's indeed correct. Moving on to question 2. Which of the following statements are true? So the first is mobile robots operates in constrained workspace. The fixed base manipulators have unlimited workspace. The mobile robot need extra sensing to determine its position and to avoid obstacles. Then fixed base manipulators have absolute measurements of position. So which of the statements are true? And please note that there could be questions that can have multiple correct answers. So any options, any answers? What about the first option? Mobile robot operates in a constrained workspace. That's obviously that's false.
It's false.
Yes. Is anyone talking? I think I might have missed. Okay, what about the second question? The fixed based manipulators have unlimited workspace. That is also
False.
I'm sorry, I'm missing actually. I'm not whomever is speaking. I'm not able to understand. There seems to be an issue with the audio. Whomever is trying to speak, I think it's Narendra, I suppose, who was trying to speak earlier. The audio was actually breaking in my. Okay. So what about the third option? Mobile robots need external sensing to determine its position. That is true, right? Yes,
It's true, sir.
we have seen that in the definition. Yes. And the fourth is fixed base manipulators have absolute measures of position. That's also true, like we have seen at the beginning of this session. So we'll check the answers. Yeah, as we have seen, the final two options are indeed true. Now, moving on to question 3, what are the current trend of the Ds in robotics, where we deploy robots? Current trend is, we deploy robots in, apart from dull, dirty, and dangerous tasks, we deploy them in domestic and dexterous tasks. So that is what we are seeing currently, right? The robots have infiltrated in domestic scene. We have, the Roomba vacuum cleaning robots and all sort of other robots. So in that case, the option is actually B, I suppose. Unless I'm very much mistaken. Yeah, it's indeed option B. You can expect mostly, for the week one, questions are mostly descriptive like this. You will get on to numerical problems, in the subsequent weeks, as you get on to week 2 onwards. Okay, so I think that's about question 3. What about question 4? For a land-based mobile robot and water surface vehicles, the degree of freedom is
3.
is it what? What is it? What is the answer?
It's 3. 3.
It's
It's
yeah.
3.
Yes, it's 3.
Yes,
It's
3.
very easy to get confused because we have seen a lot of degree terms, degree of freedom, degree of mobility, degree of steerability, degree of maneuverability. But I think we can all agree that the degree of freedom of wheel mobile robots and water surface vehicles, they remain on the surface of the water, does not go underneath it. So in that regard, it can only have 3 degrees of freedom, which are 2 positions and 1 orientation. So far so good. We got all the answers correct. Moving on to question 5, the degree of mobility of a mobile robot is, which of the options apply? The degree of freedom that the robot manipulates directly through the wheel velocity. Is that correct or not? Degree of mobility of a mobile robot is the degree of freedom that the mobile robot directly manipulates through the wheel velocity. What about the second option? It is the degree of freedom that indirectly manipulates by changing the steering configuration and moving. The third option is the total number of controllable inputs. And option 4 is always 3 for wheeled mobile robots and water surface vehicles. The fifth option is the sum of degree of freedom and degree of steerability. The sixth option is the sum of degree of maneuverability and steerability. So what could be the answer? What is degree of mobility? Should I give more examples of degree of mobility? So like as per the basic definition of degree of mobility, it's the input or it's the degree of freedom or it's the control input that that you give directly to wheel to manipulate its velocity. So like, for example, if you have a robot with 4 wheels, 4 conventional wheels, and if you are giving individual input or individual degree of freedom to each of these wheels, I'll call this omega 1, I'll call this omega 2, I'll call this omega 3, and I'll call this omega 2, omega 4. So each of these control inputs will contribute to the degree of mobility. These are fixed conventional wheels. They don't have any sort of steerable inputs. So each of these wheels are individually driven. So each of these wheels will add up to the degree of mobility by a count of 1. So since we have 4 wheels, 4 conventional wheels, the degree of mobility of this particular system is 4, basically, degree of mobility is 4 for this instance. And what about the case of, like tricycle, like an auto rickshaw? It has 2 wheels, but they are coupled by an axle, right? And it'll have a front wheel that can basically steer. So what is the degree of mobility of an auto rickshaw or a tricycle sort of a vehicle? What is the degree of steerability of the earlier example? The degree of steerability of this, 4 independent input robot?
It's 4.
No, it's 0, right? Because we are not giving any sort of steering input to any of these wheels. These wheels are fixed. Their orientation is always going to be fixed. You are only giving inputs to the wheel velocity. You are only giving the in one single input from the motors. Each of these wheels have one motor attached to it. This wheel will have one independent motor. This wheel will have independent motor. This wheel will have independent motor, and this wheel will also have an independent motor. And each of these, motors will give individual inputs to each of these wheels. So that's what this degree of mobility is. The degree of mobility is the degree of freedom or the number of control inputs the robot manipulates directly through the wheel velocity. So in this case, the degree of mobility is 4, but since each of these wheels are fixed, they are not allowed to rotate. They cannot rotate like this. The degree of steerability is 0 in this system. But in case of an auto rickshaw, or in case of a tricycle, these 2 wheels are basically coupled. The rear 2 wheels are basically coupled by a single prime mover or a single motor, like so, right? So, but the front wheel, we are not powering the front wheel. We are only steering the front wheel, right? We are only giving one input to the front wheel just for steering. We are not giving any velocity. We are not giving any active velocity to the front wheel. So in that regard, for a tricycle, the degree of mobility is 1, because we are only using a single prime mover, and since the axles are coupled, this single prime mover is driving both of these wheels. They are not individually powered. So the degree of mobility is 1. The front wheel is not, it's not actively powered. we are only using it for steering. So degree of mobility is just 1, but the degree of steerability is again 1. Degree of steerability for a tricycle is 1 because we are giving one steering input, one independent motor for steering. But the rolling velocity of the front wheel, it's completely passive. These wheels move because the entire auto is moving, or the auto rickshaw is moving. It's and the degree of steerability is 1. The front wheel does not have any mobility. And what about the case of a bicycle? This is the rear wheel. We have a front wheel like so at a different orientation. What is the degree of mobility and what is the degree of steerability? This is a tricycle. This is a 4-wheel robot. 4-wheel. We call this skid steering, actually, skid steering. We'll see this in more detail in the subsequent weeks. And this is bicycle, actually. So what is the degree of freedom of a bicycle? Sorry, degree of mobility.
1.
It's 1. Yes, correct. Because we are giving one input, that directly manipulates the wheel velocity. We are pedaling the rear wheels, which directly changes its wheels rolling velocity. So the degree of mobility, which directly changes or directly manipulates the wheel velocity is 1, because we are only powering the rear wheel. And what about the degree of steerability?
1.
That is also 1, correct. Because we are giving the steering inputs to the front wheel, but it's not powered, it's passive. So yeah, basically degree of mobility, the key definition of degree of mobility is actually the first option. The robot, it's the degree of freedom, or it's the input that a robot manipulates directly through the wheel velocity, directly through the wheel velocity through some input, through some motors or through some pedaling action. So that is the key definition of degree of mobility. So that is true. And what about the second option? Degree of freedom that indirectly manipulates by changing the steering configuration and moving. So this is actually the definition of degree of steerability. Degree of steerability. And the total number of control inputs. Again, that is not, that is not in line with degree of mobility. This can be in line with degree of maneuverability. Degree of maneuverability, because it's basically the sum of mobility and steerability. Because mobility is it's a control, and steerability is also a control, even though we are indirectly manipulating the wheel velocity. What about option 4? Is always 3 for wheel mobile robots and water surface vehicles. Is that true or false? So degree of freedom is 3, that I can agree, because you require 3 coordinates to describe its position and orientation. But degree of mobility is not always 3, right? Because here itself we have seen an example, right? In case of a tricycle, the degree of mobility is 1. In case of a bicycle, the degree of mobility is also 1. But in case of this robot, the first one that we have considered, the degree of mobility is actually 4, because we have 4 independent inputs. So that option is actually false. This is false. The previous ones are all false. And the fifth option is the sum of degree of freedom and degree of steerability. That is obviously false, because anything that has to do with sum, it has to do with degree of maneuverability. And the last option is the sum of degree of maneuverability and steerability. That is also false. So I hope we can all agree that option A is the only correct option. Right? So like if there is no conflict, we can check the answer. So option A is the only correct answer, because this is essentially the definition of degree of mobility. We have seen in the previous slides. That is degree of mobility by definition. So moving on to question 6, it's a true or false question. Legged locomotion requires lower or lesser degree of freedom and therefore is of lesser complexity than wheel locomotion. Is it true or is it false? It says legged motion is less complex than wheel locomotion. Any suggestion?
False.
It's false, obviously. So I hope I don't need any further clarification on that, because we can all unanimously agree that legged locomotion is far more complex, because in a leg, you can have multiple joints, like, you can have a hip joint. Hip joint itself has 2-3 degrees of freedom. Then you have the knee joint, you have the ankle joint, multiple joints, multiple links. So inherently, it's far more complex than a wheel locomotion, where you just require a wheel. You can probably have 1 degree of freedom to control its velocity and 1 more degree of freedom if you are required to control its steering axis. Okay, so the answer is indeed false. Moving on to question 7. So this is a numerical problem. So the input velocity command of a land-based mobile robot is given as 100. So zeta, the input that is given in the body fixed frame, it is given in the question as 100. I hope you can recall what these zeta are. These are UVR, the longitudinal, lateral, and angular velocities in the body frame of reference. And the mobile robot is oriented 90 degrees with respect to the base frame. So if I have this base frame in a y-axis, this is the x-axis. I'll call this the inertial frame of reference. And here we have the mobile robot like this. And as per the question, this is oriented 90 degrees with respect to the base frame. So the x-axis would look like this, and the y-axis would look like this, right? Because this is rotated 90 degrees. And we have the u velocity in this direction, v velocity is in this direction. So in this case, what will be the time derivatives of the generalized coordinates? So you are required to find out x dot, y dot, and psi dot. What are these? Or eta dot. Yeah, we call this vector as eta dot. So these are the time derivatives of generalized coordinates. So what are the answers for this? You can see from the figure itself, right? You can actually see from the figure itself. Given the question, you have u as 1 unit, 1 unit. So if I call this as u as 1 units, so the robot is moving u units in the local x-axis. The robot is moving 1 meter per second or 1 units per second along its local frame of reference. It will be moving along this direction, right? It will be moving along this direction. So if you consider this frame of reference, what will be the velocity if the robot is moving in the u axis? If it is moving up, the velocity with respect to the global frame of reference, it will only have the y component, right? Because the v component is 0, the r component is 0. And as a result, the robot will only move vertically upward. It won't have any component along the lateral direction, or it won't even have any, rotary component. So like this robot, it keeps on moving vertically up. And if you transpose, or if you, consider the coordinate frame of the base fixed to the ground, it'll have a velocity along this y-axis. and zero velocity along x-axis and zero velocity along the psi dot. It will have zero component along the psi dot axis. So in that regard, the correct answer just by observation is nothing but 0, 1, 0. Right? 1, 0, 0 in body frame of reference is 0, 1, 0 in ground frame of reference. Or if you want to do that numerically, you have that, the mapping, the forward kinematic mapping, eta dot, which is nothing but x dot, y dot, psi dot, is nothing but cos theta minus sin theta, cos theta. Then we have 0, 0, 1, 0, 0. This multiplied by UVR. Right? So as per the question, UVR is given. You are required to find out x dot, y dot for psi dot. And the theta, right? The orientation is also given in the question as 90 degrees. So it's a simple matter of substitution. If you substitute 90 degrees in place of theta, cos 90 is 0, minus sin 90 is minus 1, then sin 90 is 1, cos 90 is 0, and UVR as per the question is 1, 0, 0. So if you multiply this out, the answer that you are going to get is 0, 1, 0. This is nothing but what we have observed earlier. Just by observation, we have also reached the same conclusion. Right? So this will be more tricky if the orientation is not, 90 degrees. It could be some random angle, maybe 30 degrees, 60 degrees, 45 degrees. So if that is the case, you will have to, resort to this numerical approach. The forward kinematic equation. Eta dot is j of theta multiplied by theta. This equation. But if the orientation is something very simple, 90 degrees, 0 degrees, then we can directly use this correlation. Directly use this, correlation between the orientation of both of these frames. So I hope there are no doubts or queries in this. If anyone has any doubts, or if you guys are not really convinced about this answer, please let me know before we move on to the next question.
Sir, can you give the formula once again for x dot, y dot, and z dot?
Yeah, it was this one, right? I'll write it down. Yeah, we have visited that in the previous slide. So the mapping between x dot, y dot, psi dot to the velocity in the body frame, u, v, r, is given by this transformation matrix. We call this as a Jacobian matrix with this cos theta minus sin theta 0, sin theta, cos theta 0, and 0, 0, 1. Right? Where this vector, we call this as eta dot, and this matrix, we call this as j of theta. We call this as a Jacobian matrix. And this vector is nothing but the vector of velocities in the body fixed frame of reference. We call it as zeta. So I hope we are clear with this.
Yes, sir.
Okay, thank you. So we'll move on to the next question. I think we may have probably 5 or 6 questions more, short questions. So which of the following subsystem deals with the robot's execution of planned actions? So like we have seen different subsystem of robots dealing with locomotion, sensing, reasoning, control, and communication. So again, this is by definition the subsystem that deals with robots' execution of planned actions is nothing but the controller actually. So like once it has passed the reasoning phase, it will give the controller will goes into this control phase where it will give the commands to the actuators or in case motors. So based on the reasoning, based on what it basically gathers from its reasoning, it will basically devise a control strategy. How much speed should I provide to each of the wheels? How much steering angle should I, provide to each of these wheels? So once the controller has made this decision, it will pass on the control inputs. It will directly give instruction to the motors so that the robot can actually start moving. So the subsystem that deals with robots' execution of planned tasks, it's the controller, or it's the controller actually. It's by definition we have seen the definition of each and every subsystems of a mobile robot. So yeah, it's a fairly descriptive question, and I suppose we shouldn't put much effort on debating that. So another similar question. It's asking the definition of either of these. So dash of a motion system is the minimum number of variables to describe a system. So sum of one of the degree of a system is to describe is basically the count of minimum number of variables to describe that system. Is it degree of mobility? Is it degree of steerability? Is it maneuverability, degree of freedom, degree of motion, or degree of control? At least we'll just narrow it down to the to the degree term that we are familiar with. We are familiar with degree of mobility, we are familiar with steerability, we are degree with maneuverability, we are degree with familiar with degree of freedom. Right? Degree of maneuverability is nothing but degree of mobility plus steerability. Right? And what does degree of mobility stays? Degree of mobility is nothing but the input that we are supplying to directly manipulate or to directly control the wheel velocity. And degree of steerability is the input that we are indirectly giving so that we can basically steer a wheel. Right? It's basically modulating the wheel velocity, but it's not, since we are not directly giving that, that input to the wheel. We are simply modulating that steering axis. That's degree of steerability. And maneuverability is nothing but degree of, it's just the sum of degree of mobility and steerability. What about degree of freedom? Is that a good candidate for this question? So like by definition, degree of mobility, degree of freedom is the minimum number of variables to describe a system. Right? Like I've said before, for a spatial rigid body, for a spatial system, you require 6 variables, 3 for position and 3 for orientation. And for planar systems, like water surface vehicles or any mobile robots, you only require 3 degree of freedom. Right? You only require 3 variables to describe its configuration, 2 for its position and 1 for its orientation. So like in that regard, I hope you can all agree that degree of freedom is the correct answer for this question. Right? Because by this statement, by definition, is how we describe degree of freedom. The number of coordinates required to describe a system or to describe the configuration of a system. So that's by definition what degree of freedom is. Yeah. But I can understand, it's probably a bit difficult at the beginning, to distinguish between, these various degree terms, degree of mobility, steerability, maneuverability, but, there is no escape from it apart from learning learning the key definitions of it. Because, these sort of questions you will for sure, you can actually get during the weekly quizzes. But, once you familiarize yourself with these definitions, it's probably, it's not a big deal though. Okay, so yeah, the answer is indeed degree of freedom. So moving on to question 10. So I suppose this is an inverse problem, right? So yeah, the question says the vector of time derivatives of generalized coordinates of land-based mobile robot is given as eta dot. So now we are being given eta dot. So eta dot is being given, which is nothing but x dot, y dot, psi dot. This is given as 5, 2, and 1. I'll write it here, the vector of generalized velocities in fixed frame. And what else is given in the question? And the mobile robot frame is oriented 30 degrees with respect to the fixed frame, right? So if you consider this as the fixed frame, the y-axis, the x-axis, and you have the mobile robot which is oriented 30 degrees with respect to the fixed frame. So if this is xb, if this is yb, so the relative orientation between the fixed frame and the body fixed frame is, I'll call this as 30 degrees. I hope that is clear. So in this case, what will be the vector of input velocity command? What is the vector of input velocity command? So like we know the relation for that, forward inverse mapping. We know that eta dot is this j of psi or j of theta, or probably I'll just write it as j of 30 zeta. And in the question, eta dot is given. This is given. And you are asked to find out this vector theta, right? Where theta is UVR. The lateral velocity, the longitudinal velocity along XB axis, the lateral velocity along YB axis, and the angular velocity along the ZB axis. So how do you find out? You have all the information. So I'll just substitute the values. 5 to 1 is, if you expand out the Jacobian matrix, it's cos 30 minus sine 30, 0, then sine 30, cos 30, 0, then you have 0, 0, 1. You are asked to find out this vector UVR. So how do you solve this? You have to take the inverse of this matrix and pre-multiply the left-hand side with that inverse, right? So UVR is nothing but cos 30 minus sine 30, 0, sine 30, cos 30, 0, 0, 0, 1. The inverse of this matrix multiplied by 5 to 1. So if you do that, you will get the answer. So yeah, I suppose we can solve this, right? We can actually solve this. You can substitute the values, find out the inverse, and then pre-multiply with this vector. So I suppose you will end up with, should I declare the answer, or are you guys doing this live? So this is just a procedure. So in that case, I'll just reveal the answer. The answer is nothing but like once you do this calculation, you will get the answer as the fourth option, option D. Okay. Right. Now we have three more small questions. So for a conventional van or a car, considering only ground and land based, the degree of freedom is dash and the degree of maneuverability is dash. What are the answers? So I would expect you guys to, contribute for this question. So I'll draw a schematic of a car. It has, two rear wheels. And these two rear wheels are coupled by an axle. And this axle is driven by an engine, probably, engine plus transmission, whatever be the case. And at the front, you have a steering axis, you'll call this a steering axis. And it will probably have some sort of a linkage so that, the front wheels can be steered. So like you can consider this to be a two-wheel drive, only the rear wheels are powered. The front wheels are not powered. It's only steered. So what is degree of maneuverability?
Two.
Yeah, how did you get that? Can you elaborate on that?
Steerability 1 and
Yeah, you're correct.
mobility 1. Mobility 1.
Okay, that is indeed correct. Sorry, yeah. So basically, degree of maneuverability is nothing but degree of mobility plus degree of steerability. And I couldn't get your name, but as you have rightly pointed out, the degree of mobility is 1 and the degree of mobility is also 1. Steerability is also 1. So the degree of maneuverability is essentially 2, right? Because the input that is directly modulating the wheel velocities are giving from a single input, right? The single engine transmission combo is actually it's actually modulating the wheel velocities directly. But since they are coupled using an axle, you are essentially using a single input, a single engine transmission combo to power these two wheels. So the degree of mobility is 1, and degree of steerability, you have one steering input, one steering input as provided by the user to the using the steering mechanism. You are steering the two wheels, but you are only giving one input. So in that regard, the degree of steerability is also 1. So the degree of maneuverability is nothing but the degree of mobility plus degree of steerability is 2. Okay, so that is correct. What about degree of freedom? What is degree of freedom? So as per the definition, degree of freedom is basically the number of variables or inputs required to fully describe the system. So the system being a mobile robot. So like how many variables do you require to fully describe the position and orientation of a car? Like as you know, you can park or you can have your car, you can basically, take your car anywhere in any location, in any orientation, right? You can have your car at this instance in this orientation, and at some other instance you can have your car like this, which is at a different position and orientation, or you can at a different instance you can have your car like this, completely different position and orientation. So like to define a state of a car at any instant, how many inputs do you require? You can consider a global frame here, a fixed frame here, if I call this as an X, as a Y. So to describe this state, if it is a car, so if this is the frame of reference of the car, what are the two variables?
X and Y.
Yeah. But don't you require one more variable to
Z.
describe its orientation as well?
Yes, Z also.
Yeah. Z, is it a translational degree or is it an orientational degree?
Orientation, rotation. Yeah.
Yes, correct. Yes. So because if you specify this X and Y alone, you can have this position, but it can have infinite orientations, right? It can have orientation like this. It can have orientation like this. Infinite amount of orientation is possible at the specific X and Y location. So as a result, to fully describe its configuration, you require three variables, two positions and one angular coordinate for describing its orientation. So in an essence, we need three variables. So that makes the degree of freedom of a conventional car or a van to be 3. So I hope we can all agree on that. Or if you are not convinced with my reasoning, please let me know. I can, I can probably do better. So in that regard, I think the answer is option C. I hope we can all agree to that. 3 and 2, yes indeed. And the second last question, for indoor applications with engineered smooth floors, which mode of locomotion is more efficient? Very smooth tiles, smooth floors without any undulations. Which is more appropriate? Do you recommend a legged robot? Do you recommend a tracked robot, like a military tank? Do you recommend a wheeled robot? Do you recommend a hybrid robot? Exactly, yeah. So this is more recommended because others are far too complicated for a smooth surface. Legged is far more complicated. It may probably not gain enough traction. Tracked is also probably an overkill. It's mostly intended for outdoor purposes. Hybrid, again, it's not really needed. It has properties of legs and wheels. We don't really require legs for a smooth surface. And crawling type won't even probably work. They may, as you can see, lizards and snakes, they struggle in very smooth surfaces. So that won't even probably work. So the most efficient, most appropriate, most ideal locomotive solution is indeed wheeled locomotion. That's indeed the answer. And the final question, for the given below mobile robot, the degree of freedom is dash, the degree of mobility is dash, the degree of steerability is dash. So I'll describe what this is. This is a mobile robot. This is a mobile robot, and these two wheels are powered as well as steerable. Right? So the wheel at the back, it can rotate about a vertical axis. The front wheel can also rotate about the vertical axis. At the same time, it can also be powered. These are also powered with its own individual motors. So each wheels have two inputs, one for steering, one for powering, one for steering, one for powering. And these green dots are simply caster wheels. They are neither powered nor steered. Just like this, shopping trolley passive wheels. So what is the degree of mobility? Any answers?
2.
Degree of mobility is indeed 2 because we are giving two inputs to directly modulate the wheel velocities for the two wheels. And what are the degree of steerability? These two wheels can steer independently, about its own vertical axis.
It's 2.
That's also 2, yes. And what about the degree of freedom? Degree of freedom?
Mhm.
Like how many variables do you need, to fix its position?
3.
Yeah, exactly. Because like whatever be the configuration of the mobile robot, whatever be the number of wheels, for wheel mobile robots, the degree of freedom is always going to be 3. But its motion capabilities can vary, but it can have actually, it can only have 3 degrees of freedom. So the thing is, these sort of vehicles, they can actually move laterally like this, without changing its orientation. But a car cannot move laterally, right? If a car wants to move, if the car is actually, oriented is in this position, and if it has to move along this direction, it'll have to, it'll have to probably take a reverse along this path, and then it'll have to reorient itself in this path, right? But these sort of mechanisms, they can simply tilt its wheels like this, and then it can simply drive off, in this direction. So like their motion capability is different, but even though that's the case, they can still have they only still have 3 degrees of freedom, but they are far more maneuverable, than a car. They can even move diagonally like this. If all the wheels are aligned like this, and if you are powering these wheels, they can move diagonally. And if all the wheels are pointing forward, they move forward. If all the wheels are moving backward, they can move backward. And if 2 wheels are, like this, oriented like this, and if one wheel is going in this direction and the other wheel is going in this direction, they can rotate like this with 0 turning radius. So like they are far more maneuverable, but since it is a mobile robot, you only need 3 degrees of freedom to describe its, describe its configuration. So yeah, the answer is indeed 3, 2, and 2. So yeah, I think, that's it for this session. We have solved enough problems. We have also had a refresher for the contents of this week. So I hope the session was satisfactory, and we have covered 2 hours worth of, we have actually covered 2 hours for this session. So unless you have any further queries, yeah, thank you all for attending. If you have any queries, please let me know. You can also make use of the discussion forums, through the Google Meets, through that NPTEL website. You can actually go to the discussion forum, and if you have any queries, if you notice any discrepancies in the quizzes, you can always let us know, through the discussion forum, or you can also report it to me through these live sessions. So yeah, apart from that, I have nothing more to add. I'll just say thank you for attending, and until next week, I'll say goodbye. You can all log off.
Sir, can you please go to question number 7 once?
Question 7. Okay. Question 7. Yeah, this one, right? Yes.
Yeah. So from how did you write from standard frame? Like first you wrote this answer now without numerical explaining.
Yeah, without numerical explaining. Yes.
So
You want?
directly explain that.
Yeah. Okay. I'll explain that once more. So if you consider this as the fixed frame, this is y-axis and this is x-axis, right? And as per the question, it is given that the mobile robot is oriented 90 degrees with respect to the base frame, right? So this is how the mobile robot would look like. It is oriented at 90 degrees, right? So the XB would be like this, XB is actually rotated 90 degrees. So this is XB. So XB is rotated 90 degrees from this x-axis, right? If you rotate this x-axis 90 degrees, XB would be like this. And when YB is rotated 90 degrees, it'll be in this direction, right? So YB is like this. I hope you are following until now, right? Is that fine?
Yes, sir.
Because as per the question, it's given that the mobile robot is oriented 90 degrees with respect to the base frame. Okay. Now, as per the question, the question also says the mobile robot has a velocity 100 with respect to the body fixed frame of reference, right? So what does 100 means? 100 means. So 100 means it only has a component along XB axis. It does not have any component along YB axis. It does not have any component along ZB axis. Right? So if something is moving along XB, so XB is actually along Y axis with respect to the fixed frame, right?
Okay.
Is that clear though?
Yes, sir.
So it can move XB. So even though it is aligned XB with respect to the body frame of reference, this direction, this general direction, if you consider this axis, it's along Y axis, Y axis about the fixed frame.
Okay.
So 100 with respect to body frame is 010 with respect to fixed frame.
Okay, sir.
Yeah.
Yes, sir.
Okay, so I'll give you one more example. Like instead of 100, if the velocity was 010 with respect to body frame, right? Instead of 100, it was 010. How would it look like in the fixed frame? Is it possible for you to answer that? So 010 means it'll basically move along YB axis in this direction, right? So this direction, when you refer it to this coordinate frame, it is moving, it is actually in the direction of negative x-axis, right? So if you are giving an input 010 in the body frame of reference, the velocity in the fixed frame of reference would be, it'll be -100. I hope I'm not confusing, because 010 would be along YB axis. So YB axis is aligned opposite to this X axis. It is aligned to negative X axis. So that is why I have written a -100.
Okay. Okay, sir.
Yeah.
Thank you. Thank you, sir.
Thank you.
Will this recorded session be uploaded anywhere?
Yeah, these sessions will be uploaded. I suppose this the links as well as the PPTs will be shared with you.
Okay. Okay. Thank you, sir.
Yeah, this will be uploaded. Yes. Thank you.
I joined late, like at 6:30 or 7. I joined.
Okay, it's fine. It'll be uploaded anyways. I think most probably it'll be available by tomorrow. If I cannot upload it by today, I'll try to upload it by today itself. But
Sir, okay.
It'll be-
In this question, they didn't give like clockwise or anti-clockwise, no, like rotation.
yeah, if it is not given the orientation, it's generally assumed to be in counterclockwise direction. Right?
Okay.
If that sense of rotation is not specified, if it is simply given 90, you can assume it to be counterclockwise, because counterclockwise rotation is considered to be positive rotation.
Okay.
As per that right hand thumb rule, counterclockwise is actually considered as positive. If the sense of rotation is not explicitly specified, you can assume it to be in the, you can assume the rotation to be in the counterclockwise direction. So that's why, XY rotated in the counterclockwise, it will end up like this. X will end up in the vertical direction and Y will end up like this.
Okay. Okay. So thank you. Thank you.
Thank you. Okay, so with that, I am winding up. I'm stopping the recording. Thanks. Thank you for joining.